All right, we are back. This is Techmath2. We are on section 1 of chapter 8 in the red book. That is page 342. So we're diving into circles, circles. So circumference of the circle is when you go around the outside. Like if it's a figure with points on it, we call it the perimeter, like the perimeter of a triangle, perimeter of a rectangle. If it's a circle, that's called circumference, but it's essentially the same as perimeter. It's just around the outside. All right, so circumference is equal to pi times diameter. So if they give you diameter and they tell you to find circumference, you just take that diameter, 4.28, and multiply it by pi. And we get 13.446, and they only want it to tenths, so we'll call it 13.4 feet. Same dog, different fleas, 11.7 times, you actually have a pi key on your calculator. Second, and then the caret key just above the divide is pi. 36.8. Centimeters. Now this isn't in feet squared or centimeters squared, it's just the distance around the outside of the circle. So it's just going to be in linear measurement, okay? What if they give me circumference and ask for diameter? Well, now I have to, use my algebra skills, or we could solve this for diameter by dividing both sides by pi. So diameter would equal circumference divided by pi. So there we go, put it in. Circumference 14.9 divided by second caret pi is 4 point, what do they want there? Just one decimal place again. 200, so 4.74. And this one is a little trickier because you can find the diameter the same way, but they didn't ask for the diameter, they wanted the radius. So whatever we find here, we gotta cut it in half. So 7.543944,303, but we're gonna actually take that and divide it in half because diameter went all the way through from one end of the circle to the other through the center, and radius is always gonna be half of that. So just divide that by 2, and that's 3.77. And that's in centimeters, okay? Lovely, lovely. Let's take a look at 8.2. These are called central angles. Angles that have their vertex on the center of a circle, and then, their edges connect to the circle at some spot. That's called a central angle. This is called the intercepted arc, like CD is a minor intercepted arc. All right, if I shade that part in, that's called a sector. Okay. And if I go from one point to another point on the circle, that's a chord. So officially the diameter, FD, is a chord. It's just a special chord that we also refer to as the diameter, because it went through the center. So a chord that goes through the center, that gets a different name. That's called the diameter. But if it just starts on one edge of the circle, like FE, that would just be a chord. All right? So this one, we don't really need much. They said find theta. So we can do that by adding everything up and subtracting from 360. So what do we have here? 240 plus 60 is 300. So we have 300 degrees showing. So that has to be 360 minus 300 is 60 degrees. All right, which also makes sense. We could have used the 5 and the 5. The fact that this arc is 5 and this arc is 5, they have to have the same central angle. So we could have probably just used logic there instead of adding and subtracting from 360. Just said if this is 5 and this is 60, if this is 5, that also has to be 60. EF is this one. Now we're going to use that logic. Look, this is a central angle of 120 on that circle. This is also 120, so if that is 10, this also has to be 10 centimeters because the angles are identical on the same circle. And then they said, go ahead and find the circumference. Well, we can do that without actually knowing the radius or anything. Just add around the outside, so 30 centimeters. Okay. All right. Let's look at an application problem. Like, I've seen windows like this in construction where they're like arched windows. And so, and usually put some kind of very fancy molding around it. And so you wouldn't want to waste that. And so we would have to use our sweet math skills to figure out these things. Take a look at number 10. And so they have a semicircle, but it's a arch that's split into 7 equal pieces. I'm not going to try to mark them off in their 7 pieces. I'm going to mark off just one of them, EF and CD. Okay? And they have this as the center of the circle. And they give you OA, like that. And they tell you OA is 6 feet. So this is a pretty big deal here. So 6 feet from the center to the edge. All right. How long is the inner semicircle? It's broken into 7 equal parts. So now what we're going to do is there's an arc length. S is how they notate arc length. Arc length is equal to the radius times theta, where theta is in radians. So you got to go back to those first couple of chapters where we're going degrees to radians and radians to degrees. So if I want to know this arc length, I know the radius is 6 feet here, and I know it's 180 degrees. So arc length would equal 6 times, now I can't say 180 degrees. I've got to take those degrees and transform them into radians. Remember how we do that? We just multiply it by a fancy 1. In this case, 180 degrees over pi radians. Remember, 2 pi is 360, so 1 pi is 180. So we just cancel off the degrees. And now I got 180 pi over 180. Now, since it's so simple, I'm going to cancel those 180s and just say pi here. If that would have been 181 or 182 even, something I could have reduced, I'm not going to reduce it because I'm just going to leave it 182 pi over 180, cook it into my calculator, and pop it out, all right? So let's see what that works out to be. 6 times pi, it should be in the neighborhood of 18, right? 18.8, and they want it to tenths. So 18.8 feet is this entire arc length of the semicircle. Now, you could have also, instead of using this formula, we could have said, well, let's find the circumference. That would be the whole circle, and then we'll divide it by 2 because it's half of the circle. But I kind of wanted to use this to get you used to using that, so it comes in handy. All right, so now, it's because they told us it's broken into equal pieces, 7 equal pieces, we can just take 18.8 divided by 7 to find EF. So they want to know that arc length, and so we don't really need to find, the central angle or anything because they told us 7 equal parts. So we're just going to keep that 18.8 in the calculator and hit divided by 7, and that's 2.6927, but we're going to call it 2.7 feet. Okay. So on the next one here, they give us OB, B, which goes all the way to the end, so that's on the outer part. And so they want us to, again, find the entire arc. So they tell us OB is 9 feet. So we're just going to take that arc length and say 9 feet times, it's still 180, so you don't have to do that again, pi. So S is equal to 9 pi. Which is 28.3. And then they want CD, but we know it's 7 equal parts. And so that's going to be, just divide that by 7. And round, so 4.0 feet. So if you were trying to put some kind of fancy molding around this huge circular window, we'd be, 20 feet and 30 feet would be, good measurements of that. And without having some kind of weird tape measure or something that you could bend nicely around the inside and outside of the frame, it's a lot easier to go from center to edge and center to edge and use a little math knowledge and figure out the circumferences. All right, those circular things in the real world really throw us for a loop. Let's look at number 16. That's, again, they're describing a realistic problem. This is still in 8.2. And so they have a picture for us too here, where this is 5.75 inches, and we know it's 68 degrees. It's a flat metal strip that's bent to form an arc. The central angle is 68, the radius is 5.75. Rounding to hundredths, find the length of the strip. So again, we're just going to use this. Now, while I'm talking about this here, I'll also explain the process of what's going on really quick. So this is radius times theta, as long as that is in radians. So the arc length is 5.75, but now it's going to be times, so here's 68 degrees, but I need it in radians, so I'm going to say 180 degrees, pi radians. Remember, this is essentially 1, because those are the same things, and the degrees will cancel off, and I'll have 68 pi over 180. I'm not reducing it. I know it. I could reduce it to 44 90ths and then to 22 45ths. I don't want to do that because it's a waste of time. I'm after a decimal answer. So 5.75 times 68 pi divided by 180. And we get 6.8, what do they want, hundredths? 2 inches. All right? So I told you there's another way to look at this. So if you use the formula for circumference is 2 pi r, or pi times diameter. So 2r, right, 2 times the radius is diameter. So I'm going to go 2 pi r because we have r. If I found the entire circumference of this circle, it would be 2 times pi times 5.75. But then if I only wanted this piece of it, I could think of it sort of as like a test. Like let's say there was a test that had 360 degrees, 360 points, but I really bombed it and I only got 68. My percent would be 68 3/60ths. So if we wanted the actual percent of that arc of the whole circle, you're talking about 19%. It's 0.18888 forever. All right? So this times the actual circumference would give me the arc length. Okay? And so the circumference is this. That part is the circumference. And then this part is the portion of the circle that we're actually looking at. And so it's this way you're kind of using the percentage. I think it's easier to just use this formula and know that that's radians. If you take a look at what's going on here, the same thing happened. If I rearrange this, the pi would go right there, the 2 would cancel the 360 and 180, and I'd be left with exactly that. So I'm going to get 6.82 either way. That's just kind of a different way to think about it. Okay, we'll call that